Hello, and thank you, everyone. We appreciate you taking time to join us today. Microbial Insight is delighted to have Dr. Robert Borden, PE, serves as Principal Engineer with EOS Remediation and Emeritus Professor at North Carolina State University. Dr. Borden will be discussing about Matrix Diffusion Impacts on Groundwater Cleanup Time, while Microbial Insights is celebrating the 30 years being in business. It's hard to believe that 30 years ago, Microbial Insights was born. Over the past 3 decades, we have evolved into the world leader for molecular biological analysis in a variety of fields. MI CEO Dora Taggart said, "We are honored to celebrate 30 years of MBTs and is also due to the loyal customers, colleagues, and world-renowned scientists that have believed in us along the way. During this time, we have analyzed over 100,000 field samples from the sites around the world. 2021 was our most successful year in business, and we are honored to continue to serve our customers with the highest level of customer service, quality data analysis, and unbiased interpretation for the next 30 years." Dr. Robert Bob Borden, PE, serves as Principal Engineer with EOS Remediation and Emeritus Professor at North Carolina State University. His work is focused on the transport, fate, and treatment of pollutants in the subsurface, including laboratory studies, field work, and mathematical model development. Bob has developed technologies for addition of electron acceptors and donors, co-substrates, and pH buffers to stimulate in situ biodegradation of explosives, perchlorates, hydrocarbons, ethers, and chlorinated solvents. And please note that this webinar is being recorded and will be available in the resource section of Microbial Insights website within the next week. A link will also be emailed to everyone who registered for the webinar, so no need to contact us. After the presentation, we will have a short question and answer session, so feel free to type your questions throughout the presentation, and our speaker will answer as many as possible at the end. Without further ado, I will turn it over to Dr. Borden. Thank you.
Well, thank you very much. This is Bob Borden, and thank you for that lovely introduction. Today, I'm going to be speaking to you about matrix diffusion and the impacts on groundwater cleanup time. But first, let's move along a little bit. I think I can. How come? How do I? First thing I have to remember, that's why that popped up, is that much of what I'm going to be presenting today was developed as part of CERTA project ER 2529, quantifying mobile immobile mass transfer using direct push tools. Okay. Well, I'm just going to go over that background, but I just had that lovely introduction, so I can skip most of that, although you get to see the pretty picture from this past Christmas. Okay, so I work for EOS Remediation. We manufacture and sell a variety of products to stimulate in situ degradation of contaminants in soil and groundwater. Probably the premier thing is EOS Pro. It's a emulsified vegetable oil for cleaning up chlorinated solvents and explosives, things like that. But we also sell electron acceptors, zero-valent ions, pH buffers, and a number of products to help clean up sites faster. Okay. I think most of you have probably already seen this figure somewhere along the way. It was developed by Tom Sale in 2007, and it sort of shows a picture of what we think matrix diffusion is and how it affects cleanup time. As you can see from the top image, we've got a dissolved solute plume migrating down gradient through the high permeability sand. Over time, contaminants will diffuse out of that sand into the surrounding low permeability silt and get stored there. Once the source is eliminated, clean water starts to flush down gradient through the high K sand, but then contaminants will begin to diffuse back from the low-K matrix back into the sand channel. Since monitor wells principally just sample the sands, what that's going to look like in your downgraded monitor well is it's going to take longer to reach a certain cleanup time. I think most of the people watching this seminar have seen this picture before, have that kind of general idea of what matrix diffusion is. Honestly, that's where I was, I don't know, 4 or 5 years ago when we first started that project. I actually thought I sort of understood that pretty well. But then I discovered that, well, sort of theoretically I understand it, but I don't really have a good intuitive understanding of how important it is, how long it'll extend cleanup times. And that's what I really want to focus on today is, hopefully by the end of the seminar, you guys will have a sort of better qualitative understanding of when matrix diffusion is going to be important and sort of how important it is. Okay. And just for that, I'm going to give you all a quiz. I've got here 2 sites. On the left is what we're going to later call boundary geometry. It's a homogeneous aquifer overlying a thick clay aquitard. We've got a monitor well, 330 meters down gradient. Groundwater velocity is a little bit over 200 meters a year. So then travel time to the down gradient wells, about 1.6 years. The other site on the right, we're going to call that the layer geometry. That well, the monitor well is only 40 meters down gradient, but the groundwater velocity is lower. Velocity at this site is about 40 meters a year. So again, the travel time to the monitor well is about a year. Now this figure on the right, it's only got a ½ meter thick clay layer, but it's in the middle of the monitoring well screen, versus the others, a real thick clay layer, but it's below it. So I ask you all, how long would you guess, once the source is completely eliminated, how long for the TCE concentrations in your well to drop from ambient, which is 5,000, to 5 micrograms per liter? That's 3 log unit reduction. 5 years, 50 years, 500 years? Do you have any idea? Like I said, I thought I did, but I did. Apparently I did, because I didn't know the answer to that. And well, while we got a moment, why don't you all write down your guesses right now, and then we'll come at the end of the webinar and we can check your answers. Okay, what am I going to cover? So really what the focus of this webinar is trying to give you a qualitative understanding of how important matrix diffusion is. It's going to affect cleanup time at your site under your site specific conditions. I'm going to go over some general background on matrix diffusion, the physics, how it works, how you look up diffusion coefficients. I'll show some typical breakthrough flush out curves, and then I'm going to describe what one of our major contributions is, some simplified regression equations for estimating the time for concentration decline by 1, 2, or 3 orders of magnitude. I'll go over some example sites and then some lessons learned. Now in this webinar, I'm not going to be discussing decay, contaminant decay, and its effect on cleanup time. But that actually is covered in the journal article I've got listed down at the bottom. And if any of you are interested, I'd be happy to send you a copy of that. Okay, so first of all, what is diffusion? Well, I think you all probably remember from, I don't know, high school chemistry class, they talk about Brownian motion, where either for gas or a liquid, the atoms or the molecules of a compound are bouncing around by the thermal motion of the thermal energy of the liquid. That's basically diffusion. As those little particles bounce around, they're going to migrate to the left, they're going to migrate to the right. But over time, they'll migrate essentially down the concentration gradient. And that's what we call diffusion. You can calculate the diffusive flux as just the effective diffusion coefficient times the concentration gradient. And D star is the effective diffusion coefficient. Okay, so how do we calculate the diffusion coefficient? The effective diffusion coefficient is equal to the tortuosity tau. I can do this, I can point tau times the molecular diffusion coefficient dm. dm you can look up in a handbook. In college we would have looked up in the handbook of the CRC handbook of chemistry and physics. Now you go on the internet to find it. I downloaded values for the effective diffusion coefficient from the EnviroWiki over on the right. And you can see here diffusion coefficients for chlorinaethanes, PCE, TCE, DC, vinyl chloride, and ethene. And I've got them listed both in centimeters squared per second and meters squared per year. I have a hard time dealing with 10 to the minus 6 and 10 to the minus 5, so I've got them in years. And you can see here that the diffusion coefficient for PCE is about 0.03 meters squared per year versus 0.06 for ethene. So higher molecular weight compounds generally have lower diffusion coefficients. And that's because they have more mass. So when a water molecule bumps into it, since it's got more mass, it doesn't move quite as far. Now, the second thing you have to understand that affects diffusion coefficient is temperature. We can describe that by the Stokes-Einstein equation. I won't go over all the details here, but it's related to as water temperature increases, the diffusion coefficient also increases. So we get more rapid diffusion at higher temperatures. Part of that's due to the greater thermal energy at higher temperatures, but really the biggest part is just water is less viscous as it warms up, and lower viscosity results in more rapid movement of the particles. Okay, the other parameter we need to estimate the effective diffusion coefficient is the tortuosity, or tau. Tortuosity, basically, the tortuosity coefficient reflects that in pure water, the particle would presumably migrate in a straight line. In a porous media, it has to move around all the different particles. So the path line the particle follows through the sand is longer than just the straight line distance. And that essentially makes diffusion occur slower. So we have this tortuosity coefficient. Typically, tortuosity is around 0.3 to 0.7, but in well-compacted clays, layered silicates, where you've got the clay particles all lined up next to each other in a parallel pattern, you can see that the diffusion length can actually be quite a bit longer in a clay. And so you can actually get significantly lower tortuosities in compacted clays. But for most aquifer material, we're going to be in the 0.3 to 0.7 range. Okay, before I get into the details of our work, what I want to do is go through an example site. And I think probably the best documented site that I know of where people have really shown matrix diffusion to have a big impact on cleanup time is this site studied by Chapman and Parker in Connecticut. There was a high concentration TCE DNAPL source. They investigated that on the right. This is an aquifer where there's about 3 meters of sand overlying a thick silty aquitard. There was a DNAPL spill near the source, and over time, that TCE diffused down into the underlying clay. Part of the work that Chapman and Parker did to sort of understand the processes here is they took a whole bunch of soil samples and plotted concentrations versus depth. And you can see here that the concentrations are highest right at the aquifer interface, and then gradually decrease with depth. But the contaminants have diffused a good distance, 2.5 meters into the underlying silt and clay. So there's over time, there's been a lot of mass stored down in that lower clay. 42 years after the initial release, they went out and they isolated the test on the source in a sheet pile test cell. Once that happened, concentrations in downgradient wells started to decline. What I'm showing here, again from the Chapman and Parker paper, is concentration in 3 downgradient monitor wells. They're all about 1.6 years to travel time downgradient. And you can see here, like in MW01, concentrations before the sheet pile installed were pretty constant, about 2 to, I guess that's 20 to 30,000 micrograms per liter. And then, let's see, the sheet pile was installed here, and then about 2 to 3 years later, concentrations declined quite a bit, but then almost sort of plateaued out here. So now we're at, okay, so this is sheet pile was installed in 95, 10, well, I guess that's 9 years later, concentrations have declined, maybe an order of magnitude, but then they really kind of tailed out there. That's what people are talking about when they talk about how matrix diffusion can really extend cleanup times. We've eliminated the source, but now contaminants are diffusing back out of that underlying clay. And so concentrations in monitor wells remain high, or at least well above what we'd like to get to. Okay, now this is field results. Let's look at some modeling results. Chapman and Parker did a whole series of simulations written up in a State of the Science report in 2013. They used a very highly discretized numerical model with a numerical hydrogeosphere, and they simulated a range of aquifer conditions, trying to kind of understand about how the impact of matrix diffusion is and how long it extends cleanup time and so on. What I've got shown there is a cross section through the plume downgrading the source after source removal. You can see the little dotted line there is the aquifer-aquitard interface. Contaminants diffuse down into the clay deep below the interface. And now, since they've eliminated the source, concentrations near the source in groundwater near the source are low, I'd say at a monitor well 10 meters or 50 meters down gradient. But by the time we get 500 meters down gradient, there's a significant amount of mass that's diffused up into the overlying aquifer and contaminated this well. Now, one thing to point out is, look at the sort of scale of that. This bar here is supposed to be a 5 foot or 1.5 meter well screen, and this is a 10 meter well, or a 3 meter, 10 foot well screen. The 1.5 meter, pretty much all the contamination here is within the first 1.5 meters. So while there's a fair amount of mass in the overlying aquifer, it has not spread out. It's all right down here near the bottom, sort of running across the base of the aquifer. Okay, how is that going to affect cleanup times? Well, oops, sorry. Here I've got a concentration versus time plot for 3 different values. This graph is at 200 meters downrange of the plume source, so that would be these wells here. The upper line is the concentration right at the sand clay interface. For a 1.5 meter well screen, it's a little bit lower. And then for a 3 meter well screen, it's a little bit lower still. all the curves have the same kind of shape, where there's a rapid decline and then it kind of tails off. But concentration clear at the interface are significantly higher than, say, in a 3-meter well screen. Okay. These were some great results, but, well, hydrogeosphere is not a commonly used model. It takes a fair amount of modeling expertise to run these things. Happily for us, Ron Falta from Clemson University and GSI Environmental together developed this Excel-based spreadsheet model called REMCore MD. It simulates groundwater flow and solute transport in the sand by the advection dispersion reaction equation, but it's got an analytical sourcing term for matrix diffusion. Ron's shown that this model provides really an excellent match with the high resolution models, or runs much, much faster. And that's good for us, because what I'm going to show you is we ran this model a whole bunch of times. What we were trying to do, sorry, I'm getting ahead of myself. Let me first show you these flush out curves. What I've got shown on the right, again, is a sort of typical flush out curve. I think you can see the shape is fairly similar to the Chapman and Parker curves, where this axis is normalized concentration, concentration divided by source concentration. And this is time in years after source, after their initial release. Shortly after the initial release, concentrations increase rapidly, reach a maximum, and stay high for about 50 years. That was in this example, it's a 50-year loading period. Once the source is eliminated, concentrations rapidly decline. Then there's this sort of break in slope, and they decline more slowly. If you're before this slope break, cleanup time is basically controlled by the rate that groundwater flushes through the upper aquifer. Down on this bottom part, cleanup time is controlled by both the rate that water flushes through the other aquifer, but also the rate that contaminants diffuse out of the underlying clay and up into the aquifer. In our work, our key metric for cleanup was the time for concentration decline by 1 ohm, 1 order of magnitude, 2 orders of magnitude, or 3 orders of magnitude. So you can see here, T1, the time of 1 order of magnitude reduction. Well, the source was eliminated 50 years, looks like 55. So maybe took 5 years to reach 1 ohm cleanup. Maybe 40, 45 years for 2 ohm cleanup, and 200 years for 3 ohm cleanup. So while we can get pretty rapid cleanup for that first order of magnitude, getting down to 3 orders of magnitude can take a long time, greatly extending cleanup time. What I'm hoping you'll get by the end of the seminar is sort of a qualitative understanding of what causes T3 to be really large, or in some cases smaller. Okay, so what did we do? We used REMCore MD and ran it a whole bunch of times to generate a large data set. We varied, we have 2 basic geometries, a layered geometry consisting of interbedded layers of clay, sand, versus a boundary geometry where we've got a thick aquifer overlying a thick clay aquitard. We varied retardation factors, porosity, hydraulic conductivity, distance and monitoring point, a whole bunch of different parameters for each of these things, and generated values of T1, T2, and T3. And then we took those values and went and did basically a bunch of statistics on them to try to identify some patterns to all this. This table just shows you all the different parameters that we varied and the values we selected. We tried hard to cover a broad range so these results would be broadly applicable. I will say that Some of the values in the sensitivity analysis are probably outside the normal range. So there may be some extreme outliers on it. Like for example, we've got retardation factors up to 10. That would be relatively unusual, at least for chlorinated solvents. But I certainly think 2 to 5 is reasonable for a chlorinated solvent. Okay. After doing all this work, what we found is that you could provide a pretty good estimate of cleanup time with 3 characteristic parameters. The first one is the mass retention time, TM. That's the total mass of contaminant stored in the aquifer in both high and low K zones upgraded the monitoring well, divided by the mass flux past the monitor well. Now, in this matrix diffusion modeling, groundwater velocity in the low K zone is assumed to be 0. So really, it's just the flux in the high K zone. The second parameter is the ratio of contaminant mass in the low K zone to the high K zone. That gives you a sort of an idea of how much mass you've stored down there. And that term is gamma. And then the third term is diffusion time, TD. For the layer geometry, TD equals the retardation factor R for the low K zone times the diffusion length in the low K zone squared divided by 4 times the effective diffusion coefficient. For the boundary geometry, TD is just a loading period. Okay, so with these 3 parameters, hopefully I'm going to show you that we can make pretty accurate predictions of cleanup times. So what I'm showing here on the right are graphs of cleanup time calculated with RemChlor-MD versus cleanup time calculated with our regression equations. The column on the left is for the layer geometry. The figures on the right are for the boundary geometry. And you can see here, say for 3 log unit cleanup, T3, the regression, these points pretty much all plot on a 45-degree line, so that the regression equations are very good predictors of the RemChlor value. But you don't have to run RemChlor, you just plug the numbers into a simple regression equation. For 1 order of magnitude cleanup, well, we've got a bunch of these red dots here. Those red dots are for a Dom colon number less than 1. Okay, you're like, what's a Dom colon number? I'll explain that. But for a certain data set, we saw the regression model didn't do nearly as well. So we've excluded those red dots from regression. And the regressions I'm going to show you are just for the black dots. Down colon number is TM divided by TD. So when the mass retention time is less than the diffusion time, you'll have a DA less than 1, and you may get some of these outliers. You see, for 3 log unit, we really don't have any outliers. So these equations work for all the data in those sets. The formula regressions look like this down here below, where natural log of cleanup time equals the empirical coefficient C1 plus C2 times the natural log of TM plus C3 times the natural log of TD. That's for the layer geometry. For the boundary geometry, it looks similar, except now here we've got natural log of gamma. Okay, so what does this all look like when you actually plug in the numbers? Okay, so now I'm going to look at the boundary geometry first. These are the coefficients that you can either pull off this slide or get from the journal article. You can see the R squared for those regression equations varied from like 0.93 to 0.94. Pretty good root mean squared error, and these regressions were generated with about 2,500 data points each. to give you a better understanding, well, I know you can plug those in, but it's kind of hard to understand. I've used this regression equation to generate plots of cleanup time versus TM, mass retention time. And what you can see here, and now I've got plots for the median value of gamma for our data set, as well as the 25 percentile and 75 percentile. So that's the blue and the red dashed lines are sort of upper and lower 25, 75% confidence limits. And you can see for one cleanup, pretty narrow band here at 20 for a mass retention time of 20 years. Looks like cleanup time will be a little bit less than 20 years. So T1 is about equal to 1 times TM. Versus you go over here for 3 ohm cleanup, and you can see for a mass retention time of 20 years, T3 is going to be anywhere from, I don't know, maybe 300 to 600 or so years. So pretty long cleanup times. These lines aren't straight lines, so you can't just multiply TM by a constant. But I think, roughly you see T3 is going to be over maybe 20 to 40 times TM. So if you know TM, you can get a pretty decent guess of what T3 is going to be. Okay, let me go through an example site calculation. I'm going to be using the Chapman and Parker site in Connecticut as my example, just because I already showed it to you. And now for this site, we've got as I said, it's a 42-year loading period. K is equal to 20 meters a year. These are all the coefficients taken from the Chapman and Parker case. Our monitor well is going to be 330 meters down gradient, diffusion coefficient, what they used with no decay. Now, this is our sort of image. That image is what we think of where the contaminants are. Somewhere in the overlying aquifer, maybe it's diffused 1.5 meters up into the aquifer. But there's going to be a significant mass diffused down in to the underlying clay. To calculate the total mass in the aquifer, I need to know the mass in the sand and in the clay. So I need to know how far it's diffused down. The best way to do this is, well, take Chapman and Parker's data where they've got that profile of contaminant concentration versus depth. And LD, the diffusion length, is basically just the distance to the midpoint of that curve, which I don't know, looks to me about. Sorry, gang, that was our dog. I guess the FedEx guys just showed up. But anyway, I'll keep going. So in this aquifer, diffusion length looks to be about 1.2 meters. If we know the diffusion length and the concentration, we can calculate TM. However, not all of you have these great profiles of concentration versus depth. So we went up to MEMCLOR-MD. One of the outputs from MEMCLOR-MD is the total mass that's stored in the underlying aquifer. And we can calculate the effective diffusion coefficient. LD is just the locate contaminant mass divided by the contaminant concentration times distance in the monitoring point X, porosity of the locate zone, retardation factor of the locate zone. So we extracted all these values from MEMCLOR, and we plot them on this axis. And we develop a regression equation shown below here on this axis. And we plot those points along the line. Those are the red dots of the regression equation. The dash is the 45 line. You can see obviously the equation works pretty well. So we're pretty happy. And so if you need to calculate LD and you don't have soil profile data, you can use this simple regression equation. And I'll explain what all these coefficients are in the next slide. Okay, so back to my example. Okay. Hydraulic conductivity is 20 meters per day. Q in the overlying aquifer is K times the gradient times the thickness of the aquifer. Now, we've got a 1.5 meter well screen, and that's really where most of the contaminant is. So for all intents and purposes, our aquifer, or at least the aquifer zone we're worried about, is 1.5 meters thick. So the total flow through that is going to be 28 times 0.01 times 1.5 equals 108 meters squared per year. The transport velocity is going to be 206 meters a year, and so the travel time is going to be about 1.6 years. Loading period is 42 years, and since this is the boundary geometry, the diffusion time also equals 42 years. We can calculate LD here by plugging in the retardation factor, travel time, diffusion time in this regression equation, and the regression equation says LD is about 1.2 meters, which happily, for my example, matches up with the values that Chapman and Parker actually measured in the aquifer. Mass, now to calculate TM, I need the mass in both high and low K zones divided by Q. Mass in the high K zone is just X times thickness of the high K zone times retardation factor of the high K zone times porosity of the high K zone, plus diffusion length into the low K aquifer, retardation factor of the low K, and porosity of the low K. And I know I'm going fast, but it's basically just a geometric calculation of the total mass in the high and low K zones. We calculate Q over here, so TM in this case is 300. Well, I messed up here. This says 410, and this says 390. Well, I don't know what I did here. I'll have to go back and check and see which number is correct. But I think this number actually should be a 390. But anyway, 390 times 1 divided by 108, TM is about 3.6. If we're 410, maybe it'd be 3.8, but it's around there. Gamma is the ratio of mass in the low K zone divided by the mass in the high K zone. We plug the numbers in, that ends up being 0.8, and then plug 3.6 and 0.8 into this equation, and you get cleanup time. T1 is 3 years. Cleanup time to 2 ohm cleanup is 13 years, and 3 cleanup is 119 years. So you could also just plot those on those graphs. You can see here, if we read up at TM is 3.6 years, then it looks like, oh, that's about 3.6 years. And I said before, TM for the boundary geometry was about 1 time. T1 is about 1 times TM, so okay, 3, that's about 1. And for T3, if this is 3.6 years, that's 119. Okay, so that's maybe 30 or 40 times. And so I've got the dots plotted here again for TM equals 3.6. I read up, and so our cleanup time is 120 years or so. And that's kind of how you do it for the boundary geometry. Now let me go on and go, oh, okay, let's just see how we did. That's that graph from the Connecticut site. I said T1 was about 3 years. Okay, so 1 order of magnitude reduction at 3 years. That looks, no, I don't say that's a perfect prediction, but kind of plots on the line. We can't actually do a comparison for T2 because we said T2 is 13 years, but they only monitored for, well, about 9 years. So I put the T2 there, but oh, I don't know. I think I could imagine this line continuing to drift down, and maybe that T2 might work. We can't estimate, check the accuracy for T3 because, well, we don't want to wait 119 years. Okay. For the layer geometry, same procedure here. The actual coefficients are slightly different, but the way you apply them is the same. R squared's a little higher here. Here they're varying from maybe 0.98 to 0.99. But now if you look at the graphs here, well, the graphs look a little bit different. Again, for TM is 20 years, it looks like T1 is maybe 30 years or so. So it looks like, well, TM cleanup time for one log unit is actually a little bit higher than TM, so maybe 2 times TM. Versus we go over here for 3 ohm cleanup for the layer geometry, 20-year TM equal 20 years. Looks like we got a median value of maybe 50, and ranging anywhere from like 30 up to 100 or so. So maybe T3 is 2 to 6 times TM. That's quite a bit lower than in the last one. I think for the boundary geometry, T3 was 20 to 40 times TM as opposed to 2 to 6 times. So looks like cleanup times for layer geometry seem like they're quite a bit shorter than for the boundary geometry. Okay, well let's plug in some numbers again. This is another study by Parker et al. Now in Cocoa, Florida. Hydraulic connectivity was 5 meters per day. Got the hydraulic gradient, high K porosity and retardation factor, low K porosity and retardation factor. The monitor wall is 40 meters down gradient. So we do the same thing, plug in the numbers. Now here I've got a 3-meter well screen, but a 0.5 meter that is low permeability. So sort of the effective thickness on the aquifer is now 2.5 meters. So Q equals 5 times 0.013 times 2.5 equals 64 square meters a year. Mass is simply the distance times the thickness in the high K zone, retardation factor of the high, porosity of the high, plus thickness of the low, retardation factor of the low, porosity of the low. Plug all those numbers in, and you get a total mass stored of 87 square meters. TM equals mass divided by Q, 1.4 years. Now, in the layered aquifer, the diffusion length is half the distance into the layer. So if the low K layer is 0.5 meter, diffusion length is 0.25. Plug those numbers into that diffusion time equation, and you get a diffusion time of 6.9 years. Okay. Plug those numbers in the regression equation, 1.4 and 6.9, and you get T1 equals 3 years, T2 equals 12 years, T3 equals 28 years. And they plot on the graph. Again, same sort of process, but the absolute value T3 here is now 28 years. So if you go to the field monitoring data from this site, T1, and depending on the monitoring point, but anywhere from 2 to 10 years, and T3 was 9 to 18 years, to over 18 years. So again, I'm not going to say that this matches given the wide range in these values, but certainly the calculated values of T1 and T2 are within the range observed in the field, depending upon the monitoring location. Okay. One other thing I want to show you is, okay, this all worked with, but it's all based on REM4. What I'd like to do is see how this method compares to some other reasonably independent set of data. Well, Parker and Chapman, or Chapman and Parker, did a whole bunch of these simulations. I just showed you the one for the 200 meters, but they ran simulations for different geometries at different distances. And so what I did is I went into their data set, and I actually just manually pulled off T1, T2, and T3 off their curves. And I plotted them on this graph. These are the values that I actually just pulled off the Chapman and Parker graphs, versus these are the values that the regression equations generated, and they're plotted here on this line. And again, it's not perfect, but you know, they match pretty well. So I thought this was a pretty good check, and showed that our estimates are coming up, you know, reasonably close to what our resolution models would predict. Okay, one last thing I want to cover before I wrap up here is this Dom-Kohler number. I mentioned it before. Dom-Kohler number is Tm divided by Td. Well, what we did is we went in and we compiled T1, T3, Tm, and Td from that regression data set, the 20,000 measurements. And we plotted on the graphs here. Now, this is for the layer geometry, and this is for the boundary geometry. For the layer geometry, Tm divided by Td, or the Dom-Kohler number, varies from 0.001, well, maybe 0.01, all the way up to about 1,000. So it varies over quite a wide range. But what you can see here is 10 to the 0, that's just 1. For Dom-Kohler number less than 1, we get high back diffusion. Real large values here, long cleanup times. So the ratio of T3 divided T1 is large. That means you get really major back diffusion impacts. For Dom-Kohler number greater than 1, you know, there's some matrix diffusion effects, but actually for Dom-Kohler number greater than 10, you know, the T3 is almost equal to T1, and matrix diffusion is pretty small. Well, what's typical? On this upper graph here, I'm showing the cumulative density function for all the values in this curve. You can see the median value of Dom-Kohler number is about, I don't know, 5 or 6 or 7, something like that here. And so typically, at least in our data set, most of the values of Dom-Kohler number are greater than 1. And so at least in our data set, it's pretty typical to have fairly low matrix diffusion impacts for the layer geometry. Now for the boundary geometry, it's quite a bit different. If you look here, kind of the shape of this curve looks pretty similar to the shape of the curve here. But we don't have, and so for Dom-Kohler number less than 1, we get big matrix diffusion impacts for the boundary geometry. But, well, there's no points plotted for Dom-Kohler number greater than 1. Well, if you think about it, for the boundary geometry, Td is the loading period. So the diffusion time equals the loading period. So for the Chapman and Parker, that would be 42 years. If Tm is more than 42 years, then you'd have a Dom-Kohler number less than 1, or greater than 1, I'm sorry. But if Tm is more than 42 years, the plume would not have reached your well yet. So it's really almost impossible for the Dom-Kohler number to be much greater than 1, because the plume wouldn't have gotten there. Well, that's the way it worked out. And again, if you look at the cumulative distribution function, you can see the median value of the Dom-Kohler number for the boundary geometry is less than 1. Looks like maybe it's 0.2, 0.3, something like that. Okay, so again, kind of matches up what we saw before. For the layer geometry, Dom-Kohler numbers are often greater than 1, and so matrix diffusion, it occurs, but it's not super important. For the boundary geometry, it almost always is significant, but it's only significant right next to that locate layer. If you're 5 meters out into the aquifer, probably not a big impact at that point. Okay, so let's just think where we're back. Our field examples, the Dom-Kohler number for the Connecticut site was 0.09. And T3 divided by T1 is 40. Pretty high ratio, pretty major impacts. For the Cocoa, Florida site, Dom-Kohler number is 0.2. It's less than 1, but not quite as small. And Dom-Kohler and T3 divided by T1 is 9. So again, significant effects of matrix diffusion, but quite a bit lower than for the boundary geometry. Okay, so how'd you do? Did you guess? Were your guesses reasonable for these two geometries? Well, that's all I got. Lessons learned. Over 90% of variation in T1, T2, and T3 can be predicted by the mass retention time, TM, the ratio of low to high K mass, and the characteristic diffusion time. The regression equations generally provide pretty good estimates. And what I say by pretty good, really plus or minus 20 to 40%. I know you may go, well, that's not very precise, but if you're predicting a cleanup time of 100 years, I'm not sure there's a whole lot of difference between 100 years and 140 years. Matrix diffusion is most important when Dom-Kohler number is less than 1. That occurs for the layer geometry when you have a short travel time or thick locate layers. For the boundary geometry, it pretty much happens all the time, but only directly adjoining the locate boundaries. And that's all I got. If you have any questions, I'd be happy to take them right now. Did you?
Awesome. Yes, thank you so much. That was an excellent presentation. We do have several questions. Again, if you have questions, now is the opportunity for you to ask them. So please go ahead and enter the questions in your GoToWebinar panel under the question section, and we will get to them as many as we can. Awesome. The first question is asking, how does matrix diffusion in porous unconsolidated media differ from that in fractured bedrock? And also, is it possible to model this using moss flow?
Okay, so conceptually, matrix diffusion in fractured rock versus unconsolidated media is similar, and you'll get kind of similar results, although we did not consider that in our regression equations. So I would not use our regression equations for fractured rock. But I will go back and if you think about my characteristic time here. In fractured rock, the total mass stored well, you're going to have a large volume of low-K material. But the total volume, while the velocity of water flow in a fracture might be high, the actual volume of water flowing, Q, is going to be low. So TM will typically be very high for fractured rock. Well, if TM's high, then you're going to have long cleanup times. You also, total mass in the low K matrix probably will be much higher than the mass actually in the fractures. So again, this mass ratio is going to be real high, and you're going to get long cleanup times. And oh, mod flow. You in theory can simulate with mod flow, but you need to use a really, really fine resolution. Well, mod flow MT3D. But I will say Ron Falta's got a current project where they're modifying RT3D so it can do the same kind of matrix diffusion calculation that he did in REMCOR. And I think that's going to be coming out, released, say, in the next 6 to 12 months.
Okay, thank you. The next question is, what parameters do you have to measure to get the data for REMCLOR MD model?
These parameters, so you need the hydraulic gradient, longitudinal dispersivity, molecular diffusion coefficient, high-K permeability, distance from the source, volume fraction high-K material, number of low-K layers, thicknesses of the aquifer thicknesses, the loading period, tortuosity coefficient, high and low-K retardation factors, and porosities. So these are all fairly straightforward calculation parameters for modeling, but there are a fair amount. So it's not a, well, those are the parameters you need.
Okay, thank you. And the next question is asking, will REMCLOR MD or something else support estimating cleanup time of a boundary condition whereby remediation is performed over multiple years in the upper sandy zone? In other words, can you simulate diffusion of electron donor into aquitar, resulting in an aquitar pore space treatment? At the same time, contaminated mass is diffusing from aquitar to aquifer?
It could not simulate that. REMCLOR MD does allow you to simulate treatment in the high permeability zone. And you do that by basically set a zone with a higher decay rate. And it does allow you to do that. It does not allow you, now you can put a decay rate for the lower permeability zone, but it doesn't actually allow you to simulate that concentration profile. It uses this semi-analytical method. So the low-K material is sort of a black box that you can assign a decay rate to, but that's about it.
Thank you. We have a bunch of questions asking why is the mass estimating units of meter like a square meter?
Good question. And I should have explained that, but I didn't. Okay. We, in all my simulations, I assume the source concentration of 1. So volume, actually, it's all these numbers are okay. So I'll go to my calculation here. This should actually be for flow. Q should be K times the gradient times the vertical thickness times the width of the plume. But all these calculations are done for a unit width. So you can actually multiply this, oh shoot. Here. Oh, sorry about that. You can multiply this value by 1 meter wide, so you get a flux of 108 cubic meters per year. We have a concentration equal to 1. So that would be, well, 1 gram per cubic meter would then be 101 grams per year. But since it's always, all these calculations are normalized to source concentration of 1, it all kind of cancels itself out. Mass, again, would be, it's a unit width, so mass technically should be X times these values times width equal to 1. So the mass would be 410 cubic meters times a normal concentration of 1 gram per cubic meter. So that actually ends up being 410 grams. So by the fact that we have always a unit width and a unit concentration source, you get these weird units.
Okay, thank you. We only have time for one more question, unfortunately. So the question is, if the low K layers are thicker, then the cleanup time increase, is it correct?
Okay. For the boundary geometry, the longer the loading period, TL, the larger the diffusion, LD, and the longer the cleanup time, absolutely. Now, for the layer geometry, what we found was the diffusion time here, for this example site, and this is actually a fairly long diffusion time. The retardation factor for the low K material at the cocoa site was 3.9. So that large retardation factor here, RL, gives you a relatively long diffusion time. But even there, the diffusion time is 6.9 or 7 years. If we had a 42-year loading period, basically that clay layer is fully saturated with contaminant by the end of that 42-year loading period. And so whether it's 30 years or 50 years really doesn't make that much difference. That's really the fundamental difference between the layered and the boundary geometry. In the layered geometry, in most cases, the layers are fairly thin. So the diffusion time is fairly short. And if the diffusion time is small relative to the loading period, those clay layers will be fully saturated and they can't get any more saturated than 100%.
Perfect, thank you. We have a bunch of comments here about how useful your presentation was, and people are interested of getting a copy of our slides. Would you be willing to share PDF with us so we can send it to our attendees?
Sure, I'll be happy to. And again, just shoot me an email if you want a copy of that. I can't post the paper on a website because, well, that would violate copyright stuff. But if you shoot me an email, I can send you a copy of the paper.
Awesome, thank you. We really appreciate again for your presentation today, Dr. Borden, and sharing your insight, knowledge, and experience. And the subject was very interesting, and thanks for answering all these questions. So if you have more questions for Dr. Borden, you have the contacts on the screen, and you can also email us at info@microbe.com, and we will be happy to help you get the answers for you and help you with your project. And thank you everyone for taking time today, and we are looking forward to see you all again in our next webinar. Thank you.
Thanks so much.